This is section 11.6 counting principles and 11.7 probability. So first let's talk about counting principles. Here we have 4 people, Bob, Ellen, Jeff, and Monica, and they're asking us how many ways we can pick a team of 2 people. So the easiest way would just be to start with that first person. So we could have Bob and Ellen. We could have Bob and Jeff, and then we could have Bob and Monica. And then we could go to the second person, Ellen, and we could say, okay, well, I'm only going to pair her with the people after her because the person before her, Bob, she's already been paired with him, right? When we said Bob and Ellen. So Ellen and Jeff, Ellen and Monica. And then we go to Jeff and we'd say, okay, we're not going to do Jeff and Bob because that's already taken right here. We're not going to do Jeff and Ellen because that's already taken right there. But we'll do Jeff and Monica. And then by the time we get to Monica, we'd say, okay, well, Monica's been paired with all previous people when we were actually going down the line. So that would give us a total of 6 options. But if we said, okay, well, whoever is chosen first is like the leader of the team, so order matters now. Well, that would change it up a little bit because we'd have Bob and Ellen again, Bob and Jeff, Bob and Monica. But then when we got to Ellen, we would include Ellen and Bob this time because now order matters. Ellen and Jeff, Ellen and Monica. Same thing here when we got to Jeff. We'd say, okay, well, we're going to include Jeff and Bob because we don't have Jeff and Bob. We have Bob and Jeff over here. But that's different now because order matters. So Jeff and Bob, Jeff and Ellen, Jeff and Monica, and then Monica and Bob, Monica and Ellen, and Monica and Jeff. So if order matters, now we have 12 different options, right? So that's the thing that is going to be a reoccurring theme with counting principles is, does order matter or not? And determining whether order matters will help us decide how to calculate it. So here we talk about permutations and combinations. You see on this chart on the left where it says permutations, it says the number of ways to arrange things. So order matters here, right? So back on this previous slide, this would have been the number of permutations. But then on the other side, we have combinations, and that's the number of ways to choose things. So here, order does not matter, and this would have been the example of combinations. We have 6 different combinations from those 4 names, but if we're talking about permutations where order matters, well, then we would have 12 different permutations. So the good thing is that we can use our calculator for this. So you will have to decide on many of these questions whether it's a permutation or a combination, but after you decide that, you just punch it in the calculator. So on this very first question, it says use the formula for permutations to evaluate the expression. So on our calculator, let me exit back out to the main screen. So here we'll go to Run Matrix from the main menu, so press 1. Then you will press Option, then F6, and you're going for probability, so F3. And then you see permutations and the button for combinations. So that would either be F2 or F3. So let's actually write that down. Okay, so from our calculator again, you'll press Option, then you'll press F6 to arrow over to the right, then F3 for probability, and then you'll either choose the button for permutations or combinations. So here we're using it for permutations. So I'm going to press F2. Oops. Let's put that first number in first. All right, so we'll start out with the total amount in the group. There's 8 total in the group. Then we do permutation, and then they're doing groups of 6. So how many different combinations of 6 out of that, I'm sorry, I said combinations. How many different permutations involving 6 out of that group of 8? Execute it and you get 20,160. Okay, now for our second one, they want us to find the combination for out of a group of 7, combination, so F3, of 2. And we get 21 different combinations. So you see how with permutations we get a much larger number because now you're worried about order, right? So if I said, oh, well, black and yellow with combinations, we'd say, oh, just black and yellow, that's the same as yellow and black. But with permutations, we'd say, no, black and yellow is different than the permutation of yellow and black. Okay, so here's where you're going to have to use your reasoning skills, and you're going to have to analyze this to see, okay, am I looking for a permutation or combination? Remember, it has to do with order. So I'm going to put right here, order matters, so we can remember that that would give us a clue that it's a permutation. It says a medical researcher needs 29 people to test the effectiveness of an experimental drug. If 110 people have volunteered for the test, in how many ways can 29 people be selected? So the question I would ask myself is, does it matter who is selected first versus who is selected last? It doesn't, right? It's just 29 people, and there's no significance of the first person chosen versus the last person chosen. So in this case, we would be doing a combination. Now, if they said something along the lines of, well, the first person chosen gets paid a certain amount versus the last person, they get paid less, well, now order would matter, right? But in this case, it does not matter. And so that would be a combination. The second one, though, asks how many different two-letter passwords can be formed from the letters O, P, Q, R, S, T, and U if no repetition in letters is allowed. So think about it. If my password is just that, O, P, Q, oh, it's only 2 letters. So it wouldn't be O, P, Q. If my password is O, P, right? Well, can I enter PO? It would matter, right? That would not be the correct password. So this could be one password and this could be another. So in this case, order does matter. So this would be permutations. So that is the important question you want to focus on here is, does order matter? In a race in which 7 automobiles are entered and there are no ties, in how many ways can the first 3 finishers come into the race? Okay, so there's 7 automobiles and they want 3, the first 3, right? So 3, I put 3 in a group. And the question is, does order matter? Well, does order matter? If I got in the top 3 spots, it would matter to me whether I got first place or third place, right? That's going to be different. And so order would matter. So it would be a permutation. So when we go to our calculator, remember the first number we enter in is the total number and then the amount in the group. and we get 210 ways that the first three finishers can come in. Okay, so this one says to win at Lotto in one state, one must correctly select 5 numbers from a collection of 51 numbers. The order in which the selection is made does not matter. So they specifically tell us that the order does not matter. How many different selections are possible? Okay, so first off, is this a combination or a permutation? The order does not matter, so it's a combination. It's nice when they tell you whether it matters or not. And then we say, okay, the total amount is 51. You know, it's going to be a combination. And then the group that we're going to be selecting, right, the group of numbers we're going to be selecting are 5 numbers. So that is what I'm entering into my calculator. So we have 2,349,060. Thank goodness that we're able to use the calculator for this, right? Because unlike that first slide that we were working on where we were writing down all the possible outcomes, problems like these would be impossible. Okay, from a club of 25 people, in how many ways can a group of 6 members be selected to attend a conference? So it doesn't tell us whether order matters or not, but think about it, whether somebody's the first person to be chosen to attend a conference or the 6th person chosen to attend the conference, it doesn't matter because the entire group is going to attend the conference, right? So they're not saying like, oh, well, the first person who attends the conference will be like the lead at the conference. No, they just said they'll all attend. So since it doesn't matter, this would be a combination. Remember, in combination, order does not matter. The entire amount of people is 25, and the group that we're choosing, or the amount of the group that we're choosing, is a group of 6. So hopefully you're seeing that the most challenging part is definitely going to be identifying whether it's going to be a permutation or a combination if it's not given like those previous problems. But after you figure that out, it should be pretty straightforward if you're able to navigate the calculator. Okay, we get 177,100. Okay, this one says how many different 3-letter codes, so I know that that's going to be my group right there that I'm picking, are there if there are only the letters A, B, C, D, E, and F can be used and no letter can be used more than once. Okay, and they written this right here, right? But that wasn't in the original question, but order does matter because it's a code, right? So it's 3 letters, but if I put this in, and it's actually this, those are the same 3 letters, right? But they're in different orders. And so remember with passwords, it's going to matter because the order matters. So it would be a permutation. We have a total of 1, 2, 3, 4, 5, 6. And we're choosing a group of 3. We get 120 choices. An ice cream store sells 3 drinks in 3 sizes and 8 flavors. In how many ways can a customer order a drink? They want us to use the fundamental counting principle with 3 or more groups of items. So with the fundamental counting principle, you will simply multiply the number of options in each category, right? So I have 3 drinks, but they can come in 3 different sizes. And 8 different flavors. If you've ever done a tree diagram, this is basically what you're doing. So I'm not going to draw it completely out, but I have 3 different drinks. And then each of those drinks, so that's just drink 1, drink 2, drink 3, have 3 different sizes. So we're just going to do small, medium, large, small, medium, large, small, medium, large. And then each of those sizes of that particular drink has 8 flavors, right? So this is the part I'm not going to draw all the way out, but I would have 8. I don't know if that's 8. Let's pretend if it's not. I would have 8 options just right there. So just this one branch of the tree would account for 8. Then this would account for 8 more. Then this, would account for 8 more. And so you could draw it out, but then you would have to count all the end options, right? An easier way to do that is just to do multiplication. So we do 3 times 3 times 8. And that comes out to 72. Okay, so this problem involves empirical probability, which just means that it's the actual information that was gathered together from this group. So the table shows the breakdown of 98,000 single parents on active duty in the U.S. military in a certain year. All members are in thousands and rounded to the nearest thousand. Use the data in the table to find the probability that a randomly selected single parent in the U.S. military is in the Army. So when we're reading this, be careful, but they're saying, okay, what is the probability? So first off, when you're talking about probability, you'll always look for the specified group that they're referring to out of the total group. So for instance, if we were sitting in a classroom and I said, what is the probability that I select a female out of the class? Well, if we have 10 people in the class and 3 are female, then it would be a 3 out of 10 chance, right? 3 is the amount, the group I'm specifying, women. And then the total was 10, right? And then as a decimal, I could just divide that fraction 3 divided by 10 and I'd get 0.3. So that's the same thing we're doing here. So let's go ahead and underline something. They said the probability that a randomly selected single parent in the U.S. military is in the Army. So we're looking for Army, and the entire table is of single parents, right? So be careful of that because you'll see in some of the other questions that maybe we're just looking at a certain group in the table, but it's just who would be in the Army out of all single parents. Let's put military parents. Okay, so I look at, and they didn't specify whether it was a male or a female, right? So it's not like I'm looking at these individual numbers. I'm looking at the total here. The total that are in the Army is 38, and then the total amount of single military parents that they considered was 98. Okay, so that is my fraction, but they asked me to answer as a decimal, as an integer, or a decimal rounded to the nearest hundredth. I get 0.387755, yada, yada, yada. Nearest hundredth would take me 2 places out. So I have 0.38, but that 7 to the right of the 8 makes that 8 bump up. So it'd be 0.39. So hopefully that made sense. But remember, you're always looking for a portion of that group out of the entire group. And pay attention what they consider the entire group. So here it says the table below shows the distribution by age and gender of the population of a certain country. So this is the population of a country. All numbers are in millions. One person is randomly selected from among those who are male. So we're only looking, that's important, we're only looking at the males. Find the probability of selecting someone who is 50 years old or more. So 50 years or older males would be 28.4. The total of males is 72.8. Be careful because you might want to look down here for total, right? But they told us that we're only looking at the males. And so you have to almost say, okay, I'm not even looking at the rest of this. I'm only considering, I was trying to highlight that top. That's not going to let me do it. Okay, I'm only considering that first row because that's the part that has males in it, and that's what they want me to consider. So 28.4 million males over 50 out of a total of 72.8 million males. Okay, let's punch it in our calculator. We get 0.3901. It keeps going. They want us to type an integer or a decimal rounded to 3 decimal places. And so that would take me out to 0.390. That 1 to the right does not make the 0 round up. So I can even leave the 0 off. At the end, I can just put 0.39 because that 0 doesn't change it. Oops. I was trying to make my 9 clear and I made it worse. Okay, this table shows the educational attainment of the population of Mars, ages 25 and over, expressed in millions. It says find the probability that a random selected Martian, aged 25 and over, has not completed 4 years or more of college. So it doesn't specify male or female, right? They're saying looking at the entire bunch, because this entire table is Martians 25 years and older. So that can maybe throw you off too, because you're like, yeah, but they only want me to look at the ones that are 25 and over. Well, this whole table represents 25 and older. So out of the total, what are the chances that I will choose a Martian that has not completed 4 years of college or more of college? Okay, so the ones that have completed 4 or more of college are here, but they're saying not those ones, the other ones. Okay, so I could do 27 plus 50 plus 41 over 163. I can also do 163 minus 45, and then it would leave me with the remaining value of Martians. Either way, let's punch that in. Let's clear this out. Okay, it gives us 118 over 163, but we want a decimal, so I'm going to go down to this button above the A, F to D. That's just fraction to decimal and vice versa. It gives me my decimal, take it out to 3 places, 0.723, and that 9 to the right of 3 makes it round up. So 0.724 is my answer. So just be careful, because you see how tricky that got when it was saying what is the probability that we'll choose somebody who has not completed 4 years of college or more, and you might be looking for the one who has. All right, this one shows the same thing. It shows completion of college of a certain country, ages 25 and over, and they want us to use the data to find the probability that a randomly selected person from this country, age 25 or over, that is meaningless because this entire table shows us those that are 25 and older. So we're looking for those who have completed 4 years of high school only or less than 4 years of college. Okay, so let's look at what that looks like. So 4 years of high school only or less than 4 years of college. Oh, that's less than 4 years of high school. So less than 4 years of college. So be careful, because I just read the less than 4 years and I immediately wanted to go here, but that's less than 4 years of high school. They want it less than 4 years of college, so that would be this number. So 57 plus 42 out of the total. And we don't have to worry anything about male or female because they didn't mention anything about that. I'm actually going to use my same fraction bar. Just go up and change the values in there. Okay, so 57 plus 42 over 170. We get 99 over 170. I'm going to press F to D on my calculator to get that decimal. They want me to take it out to, oh, they actually want a simplified fraction here. So make sure that you're paying attention to how they want the answer. They say type an integer or a simplified fraction. So I'm going to press F to D again and get my simplified fraction. That's a 0. Continuing with probability. So this is theoretical probability. What we were looking at before was actual data. So obviously, like the completing college on Mars, that's not real life data, but they're saying, look, this was the actual information they had made up. But this is what actually occurred. So take the probability off of what actually occurred. This is theoretical probability. So it's like, hey, in a perfect world, if every single time we did the probability, it came out the way it was supposed to, what would be the probability of this? So taking a 12-sided die, they roll it, they said the set of equally liked outcomes is all the 12 sides, right? So that means if I roll that die 12 times, theoretically, I should get each of the numbers once. Well, we know in real life that wouldn't be the outcome. It wants us to find the probability of rolling a number greater than 4. Okay, so what are my numbers greater than 4? Well, that's going to be 5, 6, 7, 8, 9, 10, 11, and 12. So those 8 numbers. And then my total options would be 1 through 12, right? So these are the numbers we're specifying. And then out of the total amount of numbers would be 12. I simplify. and I get 2/3. So I have a 2/3 chance of rolling that die and getting a number greater than 4. Okay, we have a 52 card deck, and we're dealt one card from that 52 card deck. Find the probability of being dealt a king. So there are 4 kings in a standard deck of cards. So the specified group we're going after is 4, and then out of the total amount would be 52. I'm going to simplify, and I get 1/13. All right, so this one says a fair coin is tossed 3 times in succession, and the set of equally likely outcomes is given. And they want us to find the probability of getting exactly 0 heads. So basically a coin was flipped 3 times back to back, right? And then they recorded all the possible outcomes. So I could either get 3 heads 3 times in a row, I can get heads 3 times in a row. I can get heads, heads, and then tails, heads, tails, heads, and so on. So they give you all the different possible outcomes. They want us to find the probability of getting exactly 0 heads. The only option we have with no heads is if I was to get tails all 3 times, right? So the probability is going to be that one specified outcome out of a total of 1, 2, 3, 4, 5, 6, 7, 8. That's simplified, so that would be my answer. If we were to do a tree diagram like earlier, this is how we could find all the possible outcomes that way. But luckily they give you all the outcomes, and so they just want you to determine that probability. Okay, lastly, this problem says a single die is rolled twice. The 36 equally likely outcomes are shown to the right. So again, they're showing us all the possible outcomes. We're not having to actually go through and map that out. And they want us to find the probability of getting 2 numbers whose sum is 6. So I see here that the sum is 6. So if I just go across the top row, right, 1 plus 1 not equal to 6. 1 plus 2, nope. 1 plus 3, nope. 1 plus 4, 1 plus 5, yes. 1 plus 6, no. Now, what you'll notice is once you go through the rows, it makes a diagonal pattern for all the values. And in that last row, one of the dice rolled a 6, and so there's no way that I can get a sum of 6 out of any of those combinations in the last row, because it's going to at least be a 1, right, on the other dice. Okay, so we have 1, 2, 3, 4, 5 combinations that come out with a sum of 6, and then our total amount of possible outcomes, we have 6 rows of 6, so 36. And that is simplified, so that would be the answer.